Hello. Hello, Yaneli. Hello, Genesis, who has been in the waiting for quite some time. Totally noted, totally appreciated. Um, Hello, Roger, Gabriella, and Kaya. I don't know if you can hear me. I think you can hear me. There's a big thing in the chat. I apologize for the content in the chat. It's to save us a little time for me over talking it. Excuse me. I'm going to put it in the chat again because more people. Hello, people that are joining right now. Welcome back. I hope you enjoyed your holiday. I hope you all have great holidays soon when we get through this last hump. Um, we are, good afternoon, Yaneli. Good afternoon, Gabriella. Good afternoon, Kaya. Thank you. Okay. Good afternoon, you guys. More people coming. Okay. Okay. More people coming. Okay. Good afternoon, Roger. Thank you. And good afternoon, Ariana, if I didn't say. So thank you for the good afternoons. Um, so here we are. Um, Again, there are people still joining. I'm going to put a couple of things in the chat here just to save me a little. Oh, wait. Oh, good afternoon, Sydney. Thank you for saying so. Okay, I'm going to wait till a couple more. As people are coming in, I'm going to put something in the chat again. Some of you already see it because you were here right away, but if you're coming in now, you'll see something in the chat again. But good afternoon, Sydney. Thank you. And good afternoon. Okay, people are really coming in now. Okay. So good afternoon, Sonam. I love the avatar. Good afternoon, Skylar. I love the avatar. 1894. Wow. So first of all, something in the chat right here, which some of you saw. I apologize. I just want you to know that I know. It's harder than I thought these days, just managing things. But just read the chat. Your exams are definitely not forgotten, and I know how stressful this is for you. But again, the main thing is if you will get them, you are going to get them in time before your final exam. And if you're particularly freaked out, I totally understand that. And then just please text me and we'll have a phone appointment where we can talk one-on-one about whatever your situation is or whatever facts I have, right? And I can look at things right then in front of you in real time, etc. So please don't lose faith in yourself or in the situation. My summary, and again, I don't want to spend, too much class time talking about something that I don't have all the information. But I just want you to know that if you're still with me, if you're still here and still trying to do what you're trying to do and what you're supposed to do, then I'm quite confident that your academics in this class is probably better than what you think it is. That I can tell you. But again, I could be more assuring and more clear on the phone or in Zoom or whatever, just if you're not comfortable with it. And more information is coming to you. It is not forgotten and it is important. It's just harder for me than I anticipate. Um, so please bear with me. Um, Please understand. Or just call if you want to express your anger and frustration or something. Anyway, so that's one thing in terms of your midterm exams. Again, it's in the chat. I'm going to put in the chat one more time for anybody who just joined. Okay. So just look in the chat if you're wondering about your current situation. But then also so we're going to move on to we're just going to keep going with the material right now because that's the best thing we can do. Also, no, again, there's nothing new for you. I think it says it in the chat. I'm not expecting you to do anything new. Now, we're all just trying to tie up loose ends and catch up. I'm trying to catch up with you in this last home stretch, and you're trying to catch up with whatever old homeworks or revisions or anything you want to do to get more points. People have been doing that. I've been seeing it, and that's great because that's where one place I do think I am caught up with you is I think most people have gotten all points that they've asked for on all homeworks or anything. It's just the exams that I still need to complete. And some of them have started coming back, by the way. It is in motion now, so that will happen. Anyway, my point though is we have to move on anyway and finish our topics in physics before the end of the semester. The topic that one of the last topics we're going to wrap up with right now is this work in physics and energy in physics. That's one of the last topics we do in Physics 203. Um, and a couple things about that. I mean, A, whatever I'm about to talk about today and Wednesday and so forth, I would also urge you, even if it's hard or new or you're distracted or stressed, just also know this stuff is very important for the transition to Physics 204. So please save your notes is basically what I'm saying, especially if I have the privilege of having you in class next semester for Physics 204, which I hope I do, many of you, but even if you don't have me and you have someone else, but if you're in Physics 204, you're definitely going to want to understand work and energy and the calculus associated with those concepts. So that's what we're going to start lecturing about today. So please keep your notes for Physics 204. We'll hit the ground running with it then. Okay. So that's one thing. One other thing. Whoop, sorry. Hold on. One other thing. People asked in the other class, very fair question. I'm going to put something different in the chat now, please. Well, I'm going to write, if anybody hello, anybody who just joined, I'm going to put one more time in the chat. For some of you, you just saw it 3 times, but if you just joined, just look in the chat for updated information about your delayed midterm returns, for which I apologize. But look at that in the chat, because now I want to put something new in the chat in answer to a question somebody else asked me in the other class. Hold on, here we go. So what I just put in the chat is about your final exam, which of course I almost hate to bring up if you don't have your results on your midterm yet, but of course we will have a final exam. So just to be clear, and I'll put this in Google Classroom as well. If you look at the final exam, the official schedule, the other section technically would have their final exam on Monday, December 16th, and you would have yours on December 18th, Wednesday. But because I try to treat all the sections the same, and because we do a take-home exam, the same format as you did for the midterm, for good or for bad, the way we're doing it here is we're making your exam due for everybody by midnight of Wednesday of that final exam week, for good or for bad. In other words, if you want to follow the strict exam schedule, you can. You can do your exam exactly at the time that your technical John Jay final exam schedule mandates. Like, because of course they make a schedule that is meant so that you don't have a million exams on one day and so that you can distribute your time. So if you want to follow that schedule, you're absolutely welcome to. You can take your exam will be posted the week before. Uh, your exam will be posted the week before, by no later than 15, but no later than December 15th. Um, so if you want to take your exam, if you want to sit down and take it at exactly the time that the John Jay schedule says, you're welcome to do that. But the fact is you don't have to. You can take it over a period of time because it's take home. So I'm making it due on Wednesday so that hopefully you understand what I'm saying. If you have any issue with this, please write me personally. And I will put this in Google Classroom, but just so you know, your final exam will be due at the end of Wednesday, December 18th. And that's true for the other section as well. So you can work with each other in the other section. That's why I'm doing it like that. And if you have any issue or conflict, write to me directly and we'll see what we can do about that. But just give me advance notice that you have a conflict and we'll see what we can do. But if you don't communicate with me in advance, blah, blah. All right. And so it's the same as the other. Of course, I've got to get you back your midterms before you can take this thing. I understand that. But yes, the format and the expectations will be the same. Take home, open universe, etc. So I'm just saying that so that you know, so that you can start planning your life, because I know it's not too far away. And it's the ball's in my court to get you back your midterm results before we actually hit that responsibility. Oh, I'll say one last thing. Well, wait. I will also say, and then I'm going to stop and move on or make sure you. Well, wait. Are those logistics clear? Can you just raise your electronic hand if the logistics about the final exam in the chat is clear? Thank you, Yaneli. Thank you, Sydney. Thank you, Ella. Thank you, Ariana. Thank you, Samantha. Thank you, Erica. Thank you, Matthew. Thank you, Sonam. Thank you, Sydney. Thank you. Thank you. No, really. Thank you, Genesis. Thank you, Gabriella. Thank you, Brandon. Okay. That's good enough for and everybody else. I'm seeing it. Okay, great. Okay. Other thing about that, I'm saying off record. Well, I'm saying on record. I'm saying on a recording. Just so you know too, because I understand that it's causing anxiety to not have your midterm scores back. Believe me, I understand that. It's causing me anxiety, as you can see. Um, so I'm going to do something that I sometimes do. I don't always do this, but I will. I'm going to tell you right now, I have to count both. We have to have both the exams. That's just the way it is. And they have to both count because we don't have enough exams to drop one or something like that. But I will tell you right now on this recording that whichever one you do better on, I will count more in your average. I'm straight up, like not a million times more. But and I'll show you the exact algorithm. It'll be the same for everybody. It'll be clear on an Excel spreadsheet that you'll get at the end. But whichever one, so if it turns out that you did really well in the midterm, it'll count for you more, and you don't have to worry about then suddenly surprising yourself and messing yourself up in a big way with with a tough final, and vice versa. If it turns out that you didn't do well on the midterm, but there's not a lot of time for you to rectify that particular situation or it throws you, just know that if you do better on the final exam will count more for you. I will, whichever, for each of you, whichever you do better on, I will weight more heavily in your average. I've done that before and I will do it this semester. I mean, it doesn't, okay, just know that. So I'm here for what, so just the whole idea and the whole course is I'm trying to take whatever your best work is at any time and trying to lean in and have your best work count the most possible for you, whether it is your participation in Zooms or your homeworks or your one exam or the other exam or like the idea. That's why the grading system is complicated and it's hard to tell from Google Classroom where you are at any moment in the course, which I apologize for. Like, I know that, but the reason it's complicated is it's designed so that whatever you give me that's your best matters the most in your final outcome. That's the idea. I hope that's clear. So again, and if Sonam and Matthew, if your hands are still up from before, thank you. But if they're up for questions, please ask. Or no, okay, they're just up for, or Ella, a question or just hand up still from before. No, or Ella, you're good? Or okay. Um, but again, I cannot emphasize enough. It's in the chat. If any of, because I know some things are confusing. And if anything is confused, just text me at the phone. And you could email me too, but it's like fastest. If you just text me and say, I'm nervous. I would like a phone call to be reassured. Done. We'll do it. And like, we'll sit down and clearly go over your situation. And I'll admit to you what I still don't know and should know, but I'll tell you where I think you are, whoever you are, and we'll go from there. I just want, the bottom line is I'm as interested in your success as you are. Well, maybe not, but okay. Anyway, whatever. And it makes me nervous to not have you know everything. All right. Anyway, you get my point. I'll move on. But Ella, you're fine, right? Can I lower your hand? Is your okay? Well, I'm gonna move on to the new material now. So here we go. Wait a second. Okay, changing the view. So what we're getting at now. um, I am going to assume. Okay. What I want to define now is work in physics. There's a homework about work done by a constant force. Okay, again, it was assigned sort of prematurely. Those of you who did it, you got at least 20 points already. If you want to get the rest of the 4 points, just if you as I start to talk about this, if you see that you made any errors or anything, just fix them. Or if you don't think you made errors, just resubmit it and you'll get all the 24 points. Some of you have done. Oh, and quick also reminder on homeworks like that. If you've done homeworks and you didn't get all the points and you're like, I don't know what I did wrong, and especially if you're concerned, you're still trying to figure out what you're supposed to improve for the final or whatever. I would say the main trend that I'm noticing, okay, sorry, as you can see, I'm still a little bit. The main trend that I'm noticing in like old homeworks that are coming in or old homeworks that are being fixed or the
I
midterm.
just
Oh, sorry, yeah. Oh, no. Okay. Okay. The main trend that I'm noticing, the biggest thing I would say for all of you to look out for, if you're wondering like, how can I improve in time for the final? I don't even know what feedback, like I don't even know how to improve. What is he looking for? Like fair question. Oddly, I would say the main thing in a weird way for many of you, the biggest thing of all to try to focus explicitly on when you're fixing these homeworks or going into the final exam, the main thing is for sure the five-step method, but specifically the five-step method of solving problems, but specifically step two. I know it sounds odd, but if you're looking for a concrete thing to look back on your homeworks and see if you did it right or not, or look back on your midterm and see if you did it right, one of the biggest things that will help you on the final exam and in getting all the points on any back homeworks is making sure that like every single problem you solve, every part of every problem has a clear step two. What is step two? Step two is WIQ. What is the question? Like, oh, okay, no problem. Thank you, direct chat person. Got it. No problem. Awesome. Thank you. Step two is like the easiest thing to overlook and to think is just like stupid. It's the easiest thing to overlook and not do, but it's like among the most important things for me to actually get your grading done and to be able to follow what you're doing and get it back to you, especially under challenging conditions. And oddly, it's one of the more important things for you guys going on in research or graduate school or jobs, like being able to get in the habit of clearly stating what the question is in your own words or your own symbols before you move on and try to answer it is I'm just admitting to you right now, especially the farther behind I get in looking at your work, the more I look for that because I can't like cross correlate between what you're doing and what the original assignment is. That's the whole idea is you want to create a document that just does physics for me, that just says, here's what I'm trying to do. And now I'm doing it. And here I did it. So step two and step five, where you final answer circled. Step two, it seems so unnecessary. I know it does. It did to me for years. But to stop and make it clear, this is the question in my words. And here I go trying to answer it. I cannot tell you how disproportionately that will help your grade on these work on this homeworks and on tests and help me get it back to you faster. If you just really emphasize step two of the five-step method. And then think of step five as where you circle back and literally, like maybe even get an habit of drawing an arrow from step five back up to step two and saying, here, I closed the loop. There it is. You asked me to do this, and I did it, and there it is. Anyway, so that's okay. So, sorry. That said, what we have to talk about now is this concept of work in physics. Now, here's the equation in yellow in the middle of the sheet. The equation for work is force vector dot displacement vector. In huge, broad terms, in huge, simplified terms, work is force times displacement. In a way, the simple version is that simple. The simple version is that simple, that work is force times displacement. However, well, I'm going to say it one more time. Work is force times displacement. I'll even say it a little bit more specifically. 1 joule of work, Joule, like as in chemistry and all that, like as in 4.18 calories and all that business. 1 joule, it's not a coincidence. 1 joule of work is 1 Newton of force times 1 meter of displacement. In a way, it's that simple. Like the more, so, okay, I'll even say more. So, in really broad terms, you work on something is to push or pull something through space. To do work on something is to interact with something and displace it, change its position. In broad terms, that's what doing work is to interact with something, to push or pull something and get it to move. The more you interact, the harder you push or pull it, and the more you displace it, the more work you've done. If you don't push or pull something at all, you haven't done any work. And no matter how hard you push or pull it, if it doesn't move, you haven't done any work. So in really broad terms, you could say in physics, work is like, you could say is like the product of effort or interaction with result. If you see what I'm saying, like, like work is multiplication. It's not addition, it's multiplication. And when you multiply any number by zero, you get zero, right? So if either the displacement or the force is zero, then the whole work is zero. So in broad terms, to do work on something is to push it or pull it and to get it to move. That's what it means to work on something. 1 joule of work is 1 Newton times, 1 Newton of force times 1 meter of displacement. Now, that's the big broad terms. However, you can see by the yellow equation in the middle that there's more nuances than that. There's actually a lot more nuances than that. What I'm defining here in the yellow, sorry. Oh. Sorry, direct type. Just pause for 1 second. Sorry, 1 second. Sorry. Wait, people are coming in and out of the chat, I guess. Okay. Just totally lost my train. Okay. What I'm saying in the yellow is that I want you to notice this carefully. I'm not actually defining work yet. I'm first defining a little bit of work, which sounds like a very vague concept, but it's not. I'm defining so I'm using this delta, this little triangle, ultimately to mean of something like little bit. I'll be more specific in a moment. And I'm specifically saying that a little bit of work is a certain kind of product between two vectors, a force vector and a displacement vector. And it turns out that when you multiply vectors, there are nuances. You have to be careful. We have to be careful about how we multiply vectors. And there's different ways of multiplying them. One way of multiplying vectors is by doing something called a dot product, signified with this dot here. So I have to unpack some of these details like right now. Okay. First of all, so the first thing I'm saying right now is that I am not yet defining work in general. I'm first defining little bit of work. And I'm defining a little bit of work as the dot product of a force vector with a little displacement vector. So it's now my job to all of you to be more clear about, first of all, what I mean by this little and what do I mean by that delta sign? And then ultimately, what do I mean by dot product? Now stop me. So I'm about to do some math now. Okay. I'm going to get into the math in general of these symbols and then apply them back to physics. So first of all, number one, what do I mean by little? What do I mean by this yellow triangle? Okay. So I'm being mathy now. From here on in, say Z is some generalized arbitrary variable. Like Z could stand for any variable. It could stand for X, it could stand for Y, it could whatever, just any variable at all. Then from now on, so I'm being, again, mathy. I'm not specifically talking about displacement or velocity, just any variable. So from now on, if we say delta z, what we mean is a small but finite difference between two values of z, whatever z is. So if you look to the side up in blue, for example, I mean, like from your math classes, like when you said slope in math classes, slope is delta y over delta x, right? You were specific, delta meant difference. Delta y means rise. What does rise means? It means difference between two values of y. What's delta x? Run. It means difference between two values of x. But it really means difference. It means that even though the difference could be very small, and it generally was once you're like zooming in on some little section of a big graph, the delta x or the delta y could be really small, but they were still big enough to be finite, meaning specifically when we say delta y means rise, we mean there's actually a value for y2 and there's actually a value for y1, and they actually are different. And we can literally subtract one from the other with normal everyday math, normal everyday arithmetic, and get an answer, and we call that answer rise. So what I'm saying is we use delta in math and physics. Whenever a difference between two variable, whenever the difference between two values of a variable is small, but big enough to be finite, big enough to be measurable, calculable, noticeable, countable, quantifiable. That's what delta z means. Like, as opposed to what? As opposed to, you might recall, you realize that you hit a point in your calculus classes, and in some sense, in earlier in this physics class, you hit a point where you were then asked to examine differences that got so small that they were infinitely small. Not zero small, but infinitely small. Very subtle distinction, right? Like you were ultimately asked in your calculus classes to start looking at something called dx or dy or d anything. So I'm calling it dz to mean d anything. When you switch from the delta to the d, it's not a coincidence. We're still talking about deltas. We're still talking about differences. But delta, like the triangle, we use when we mean a small but finite difference. And D, we use when we take delta Z to the limit as it approaches zero. When we get arbitrarily close to zero without actually getting to the value of zero, when we bring 2 points so close together that there's still 2 points, yet the interval between the 2 points is too small to quantify. That's a very subtle zone. That's the calculus zone, right? When 2 points are still 2 points, they're not so close that they've become 1 point, but they are so close that we can't tell how far apart they are. That's called the limit as their interval approaches zero, right? And that's when we start using D instead of delta. I'm just trying to emphasize right now that delta Z means a difference in two values of Z, whereas DZ means a differential, an infinitely small difference in two values of Z, right? So like delta Y over delta X is slope. dy over delta Y over delta X is slope of the straight line connecting any 2 points. dy over dx is slope at a point. It's the slope of the tangent line to a curve at a point, right? It's the slope when the 2 points are so close together that they almost look like 1 point, but they aren't. That's what D means. So long story short, right now, at this moment in the physics class, what I'm saying is right now, I'm defining work over a small but finite interval of space. I am right now looking at the product of a force vector with a displacement vector in the case where the displacement vector is really, really small, but finite. What do I mean? Like, but really small, but not so small not to be a number. Specifically, what I mean, so in math terms, what I mean is when I say delta z, I mean it's finite, but it's too small. It's small, it's large enough to be finite, but it's too small to detect any variation in any related variable. What? What I mean in physics, and tell me if you want me to go back, but what I mean in physics terms, now that I'm going back to work now, I'm trying to be physics now. If I say that delta W is F times delta X, I mean that I'm talking about situations where delta X is too small to allow for any variation in the F. Like in my mind, I'm saying, again, to back up, this might be getting too obscure for some of us or too esoteric. Backing up, I'm saying, in general terms, work is force times displacement. Okay, in super general terms, work is force times displacement. But we have to be careful. What we're really saying right now is a small amount of work is a force times a small amount of displacement. And then you say, what do you mean small amount of displacement? And I say, I mean a displacement that is small enough that the force is one number. It's small enough that we have one number for the force to multiply by. That's what I'm restricting myself to right now. Like I'm admitting I'm not quite, if the displacement gets big enough that the force starts changing, I don't yet know what to do to calculate work. If work is force times displacement, what do I do when there's more than one force? I'm not sure yet. But if the displacement is so small that there's only one force, then I multiply displacement by force to get work. That's what I'm saying so far. I'm going to pause for a second. I know that's like a lot, as usual, it's like a lot of words to say, like very little. Can I just pause for a second? Can you just raise your electronic hand if even if you're, can you just raise your hand if you're good for me to move on? Thank you. That was fast. They're like, yeah, we were good 20 minutes ago. Yeah, wow, you were really good. Okay, okay. All right. Noted. All right, so I'm going to move on. All right. So that takes care of the small bit. So that's why I'm using the deltas right now but now, yeah, so summary of what I'm saying so far is this sheet right here. Thank you guys. Like seriously. Okay, so the summary is this sheet right here. So work is the product of the force with displacement as long as the displacement is small enough to allow for one quantity of force. Okay, so that's one issue. But here's the other nuance, the other issue that's also tricky is that, okay, but the thing is, I'm saying multiply, multiply, multiply. And yes, in really simple terms, you multiply the amount of newtons by the amount of meters and you get the amount of joules. So in fact, let me be simple so like, yeah, like, like if there's a box on the floor and I pull the box with 100 newtons of force to the right, and I pull the box 5 meters to the right. So in super simplest example possible, kind of like what the homework sort of started looking at, but not really. If I have a box, I pull the box purely horizontally with 100 newtons of force, and the box moves purely 5 meters of pure horizontal displacement, then it would be 100 newtons, and say nothing ever changed and all that. 100 newtons of force times 5 meters of displacement would be 500 joules of work. End of story. Like that's how much effort I put in. That's how much result I achieved. That's how much work I did to the box. But the catch is, the next difficulty is, wait a second. Force and displacement, strictly speaking, are vectors. Force and displacement both have magnitude, but they also have direction. So what's going on with direction? Like honestly, what we talked a lot about in the first half of the semester is how to add and subtract vectors. We never talked about multiplying vectors. What does it mean to multiply vectors? How do you take into account direction when you're doing multiplication? That's a very important question that needs to be addressed. Um, so, so, so let me address that. Okay. I'm, oh wait, oh, and Matthew and others, sorry, is your hand still up from before or is it a question? Sorry. Okay. Okay, great, great. Also, forgive me, as long as I just interrupted myself again, I'm going to put something in the chat again that most of you have read 50 times already. It's just in case anybody's coming in and out with bad Wi-Fi or whatever. Forgive me, I'm just putting something in the chat again. You can ignore if you've been here the whole time. Hold on. Hold on. It's that and two. Sorry. Okay, again, the two things in the chat are just in case anybody just came in. You can ignore it if you've been here the whole time. All right. So now I'm saying when we multiply these two vectors, the force vector with the displacement vector, in order to get the work quantity, we are doing a specific type of multiplication of vectors called dot product. There are different types of vector products. We are doing one in particular to calculate the work. So let's assume, so I'm being mathy again now. Assume you have two arbitrary vectors, vector A and B. They could stand for anything. And say they just arbitrary, they have two different vectors pointing in two different lengths in two different directions, right? Well, it turns out there's three different ways that multiplication can occur in the world of vectors. When you're dealing with vectors, there's three different ways that multiplication can occur. The first way is scalar by a vector. Now, we're actually doing this all the time without even realizing it. Anytime we construct a vector or consider a vector, if we take a vector and we multiply it by a pure scalar, if we take a vector and we multiply it by a pure number, that's like taking an arrow, which has a certain size and direction, and then multiplying it by a certain size. What happens to the arrow is it just changes its size, right? If you have an arrow that has a certain size and a certain orientation, if you multiply it by a pure number, you just stretch the arrow up or you shrink it down. You keep its direction the same. If you take an arrow of a certain direction, a certain size, and you just multiply it by a size, all you do is you keep the arrow's direction, but you change its size. What have you done? You've scaled up or scaled down the arrow. That's why pure numbers, pure magnitudes are called scalar quantities, because they just scale pre-existing vectors. So in other words, what I'm saying is you can always take a vector and multiply it by a scalar. And whenever you do, you just get a new vector, a vector of the same old direction, but a new size. We do that all the time. That's called scalar by vector multiplication. There's no like fancy word for it. And it always yields a vector. Okay. And we do that all the time without even thinking about it. Every time if we say that a velocity, someone's slowed down or something, then you just take the velocity vector. And if you say someone slowed down by 50%, you just take the velocity vector and multiply it by 0.5. Same velocity vector, just half as long. But now, more to the point here in this context right now, if you have two vectors, like vector A and vector B, like I just drew on the other page, and you want to multiply them by each other, there's two different ways of doing that. One way of multiplying them will yield a scalar result, and one way will yield a vector result. And it's always a choice. You can always do either one. How you know which one to do depends on the physics context. Like like in other words, just like in regular numbers, you have the number 3, you have the number 2. You can multiply the two numbers and get 6, or you can add the two numbers and get 5. Which one you do totally depends on what kind of situation you're trying to analyze, right? But like, right? So same thing with vectors. Anytime you have two vectors, you can dot them together to get a scalar product, or you can do what's called cross them and get a vector product. Now, in the case, and I'll say, sidebar, you can take a force vector with a displacement vector and you can cross them and you'll get something that means something in physics called torque. That's a thing, and it's a vector. That's a thing. That's not the thing that we're interested in right now. What we're interested in right now is we're interested in taking the scalar product of a force vector with a displacement vector. In other words, I'm saying work is the scalar product of a force vector with a displacement vector. Notice the way I keep writing the equations, like even here at the top of this page. The delta W does not have an arrow over it. The F and the delta X do. Specifically, when you calculate number of joules of work, you're figuring out an amount of work that is done due to a force vector and a displacement vector. You're not getting a vector, you're getting an amount. So how does that work? Because you're doing a thing called a scalar product. How does the scalar or dot product work? It works like this. The dot product between, so this is what we're talking about now. So I'm saying work, technically a little bit of work, is the dot product of a force vector with a little displacement vector. What is the dot product? It's dot is one dot product means the same thing as scalar product. They're synonymous. It means the type of product between two vectors that yields a pure number. How does it do that? What it's saying on the screen here, it measures the extent to which the two vectors lie on the same axis. The dot product measures the extent to which the two vectors are on a number line. In other words, the dot product produces a pure number by looking at the degree to which, the extent to which the two vectors are really relating as numbers. I'm going to turn the page in a second, of course, but I'm saying, like, well, I'll just turn the page. So say you have these two vectors, A and B. Again, this is a math thing. Say you have two vectors, arbitrary size, arbitrary direction. So they're related by an angle theta. Like if I put the acute angle theta between the tails of the two vectors, that's what I would mean by theta. So the dot product of the two vectors is the length of one vector times the length of the other vector times the cosine of the angle between them. That's a definition. Notice it's a triple equal sign. Notice, I mean, I'm being very careful about this. Notice one thing. Whenever I write A with an arrow over it, I mean the vector A, the full quantity, the magnitude, and the direction. When I write A without an arrow above it, I mean the length of the vector A. It's not a typo, in other words. I'm not trying to be careless. Well, of course, I'm not trying to be careless, but I'm saying, like, look off to the side here in yellow. When I write just A without an arrow, I mean the magnitude of the vector A, right? And similarly with B. So I'm saying the dot product, the scalar product of two vectors, A and B, is the length of one vector times the length of the other vector times the cosine of the angle between the vectors. Why? Where did cosine come into this? What's he talking? Like what? Wait, where did cosine come in? Because sine super, cosine crappy, if you like, or sine super. I mean, memorize. Like if you remember anything from the unit circle, or you try, sine is super, cosine is counterintuitive. What do I mean by that? I'm not trying to confuse you, or cosine is confusing. I mean, sine of zero is zero. Just as you would, if you had to invent something, sine is easiest to remember. Sine of zero is zero. Sine of a small angle is a small number. As the angle gets bigger and bigger, the sine gets bigger and bigger. That's the natural one that we would all make up if we were on a desert island and making up trigonometric functions for fun, right? The sine does what you think it should do. Well, at least what I think it should do. At the sine of zero is zero. As the angle gets bigger and bigger, the sine gets bigger and bigger. Cosine is the opposite of that. Cosine is counterintuitive, or cosine is confusing, or cosine is crazy, whatever you want to say. I'm saying, but not really. Of course, cosine's not really. It's totally logical. Ultimately, it's totally necessary. But I'm saying at first it's confusing. What do I mean? I mean that the cosine of zero is one, right? I mean, just look at your unit circle. I mean, ultimately, this is all about the unit circle. But if you can't memorize the whole unit circle or forget, just remember the sine of zero is zero. The cosine of zero is one. And as the angle gets bigger and bigger and bigger in the first quadrant, as the angle gets bigger and bigger, the cosine gets smaller and smaller, right? That's confusing at first. That's the harder one to remember or keep straight. But now you might start to see why that's really useful. In the context of a dot product, cosine is the trigonometric function that is measuring parallelism. Cosine says the more parallel two angles are, the more parallel two vectors are, the smaller an angle is between them, the bigger the cosine. So, and remember, all cosines and sines are always fractions. They're decimals, right? They're numbers between 0 and 1. So think of the cosine as like a multiplying factor, like a percentage factor, like a scaling factor. What cosine is saying is the smaller the angle, the more parallel the two vectors are, the more closer they are to parallel, the higher the percentage we're going to multiply their length product by to get their full dot product. We're saying here, and I'm going to show you an example on the next page, but just try to bear with me for a second. I'm saying in the limiting case where two vectors are purely parallel, where they lie on the same number line, the angle between them is zero. So the two vectors that lie in the same number line or the same axis are literally like just two pure numbers on a pure number line, just like homework 1 from this whole course, right? So the dot product of two vectors that lie on the same axis is the length of one vector times the length of the other vector times 1. It's just literally one number times the other number. If the two vectors lie on the same number line, multiplying them is just like multiplying numbers on a number line. We're saying it doesn't matter if they're parallel, direction is not coming into play at all. They're totally in agreement with each other. They're both affecting each other fully. Neither one of them is deviating off the axis that the other one is on. So they're both contributing fully to their full product, right? If two vectors are parallel, their dot product is the length of one times the length of the other times 1. Whereas if two vectors are purely perpendicularly, if they're lying on two completely different axes, if one vector is on the x-axis and one's on the y, then the angle between them is 90 degrees. So the cosine of the angle between them is 0. So no matter how big they are, what we're saying, what the dot product is asking us, how much are these two vectors actually affecting each other? How much are these vectors lining up like numbers on a number line? If they are not lining up at all, if they're on two different axes, they are in two different coordinate systems. Galileo, right? They are obeying independent sets of physics laws. So the dot product of two vectors is looking at how much can we treat these vectors like pure numbers. If they are purely perpendicular to each other, I don't care how long the vectors are, it'll be the length of one times the length of the other times 0. They have no dot product at all. And if they're if they're parallel on the same axis, then we'll get the full-bodied 100% dot product. Anything in between, the closer to parallel they are, the higher the cosine will be, i.e., the smaller the angle, the higher the cosine, the bigger percentage of a dot product we'll get. I hope that sort of makes sense. I'm going to do an example in a second, but bottom line, I'm saying to everybody, cosine measures parallelism. And dot product is meant to measure parallelism because dot product is of two vectors is asking us how much do the two vectors actually agree with each other? How much do they actually affect each other on the same axis? How much can we ignore the issue of directional disalignment and just deal with their directional agreement? That's what that's what the dot product does in math in general. I will apply this to physics in one page, I promise. But if you're following me at all, you might guess or imagine that, of course, the cross product, which matters a lot more in physics 204, just to complete this picture, the cross product does the opposite. The cross product cares about direction. The cross product multiplies two vectors in a manner that produces a vector. So the cross product cares about direction. Therefore, it cares how much the two vectors are affecting each other directionally. So the cross product takes a sine of theta rather than a cosine of theta. I'm just saying that to complete the whole picture for you. And you'll need to know that for physics 204. Like, please make a note of it. Cross product of two vectors is A cross B equals AB, A length times B length times sine of theta. If you want to make a note of that for physics 204, please do. And if you want to screenshot it and submit for points, under the note-taking portal, please do. But the reason I'm not writing it down is I don't want to confuse you. That just completes the picture. But what we care about here right now in physics 203 is how the dot product then generates work. And that's on this page here. So I'm going to pause for a second. Are we still cool? Can I go like, just raise your hand if I can still move on, or raise your hand if you're cool for me to just keep going. Thank you. You guys are very fast about that. And it means a lot. I'm going to take that to mean I should probably go faster in general. You get to write me in the direct chat if you're saying I should go faster in general. I'm noting it. I mean, I might not be able to do it, but I'll try. Okay. Okay. So again, summary. So now we're back to physics, right? So summary, I already mentioned, like in general, units wise, work units are measured in joules, Joule, like in chemistry. And by the way, if you think in chemistry, wait, I thought in chemistry, joule was a measurement of like some kind of energy or heat. Yes, because ultimately this all relates to energy. Ultimately, yes, it's all related. Ultimately, it's not arbitrary. It's not. I'll get there. But if you're relating this at all to chemistry or trying, good job, good idea. You should. You'll see the relation more and more. But okay, so 1 joule in general is 1 Newton times 1 meter, like even putting aside all this vector stuff. But now, how does it relate to all this vector stuff? Well, we're saying now, I know the example's a little bit squeezed, but like, say now we've got this box. Excuse me. Say I've got a box of mass M on the floor. And I'm moving the box purely horizontally along the floor. Like the box is being displaced along an x-axis, 5 meters, right? But now let's say the example is that even though it's being displaced purely horizontally, let's say I'm pushing it at an angle. Why? Just because I'm a human being, like just for leverage purposes. Like the box is on the floor and it's hard for me to like kneel all the way down on the floor and get next to it horizontally. So like I'm pushing it from above, let's say, on an angle. So at an angle of 60 degrees as measured from below the imaginary horizontal line, the x-axis, right? So say my force is 100 newtons in magnitude, and the displacement is 5 meters. In the old case that I just said vocally, if I had been pushing purely horizontally with 100 newtons and it displaced purely horizontally with 5 meters, then the work would be 100 times 5, 500 joules of work. But here, what I'm trying to say is no, 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 no. The dot product, we're using a mathematical dot product to calculate this physical concept called work. And the reason we are is because we're really ultimately saying, remember Galileo's principle. A two-dimensional problem is really two one-dimensional problems occurring simultaneously, yet independently. In other words, if I'm pushing at an angle, I'm pushing somewhat over and somewhat down, but only the somewhat over amount of my push has anything to do with the over amount of the displacement. Like by pushing down on the box, I might be doing that because I'm a human being, because it's easier for me to stand up rather than sit down. But by pushing down at 100 sine 60, that's not doing anything to contribute to the horizontal displacement of this box. So all I want to count when I'm calculating work is the horizontal display, the horizontal component of my push, 100 cosine 60, right? The adjacent side of that triangle. So I'm saying that work in general is like 100 is like force times displacement times the cosine of the angle between them. Because in effect, if you look at it in this way, in this picture, what I'm really saying, I mean, multiplication is commutative. What I'm really saying is it's like horizontal component of force times horizontal displacement. I'm only counting the component of force that lines up with, that is parallel with the actual displacement. I'm only taking the piece of the force that allows me to treat the two vectors as though they really are two arrows lined up on one number line. I'm getting rid of any directional aspect that is not aligned. Hopefully that makes sense. So the total work that I'm doing in this case would not be 500 joules, it would be 250 joules. The cosine of 60 is 1/2. You can check on a calculator. So the total work is 250 joules. And notice, it's literally 250 joules. It's a scalar. It's not like to the north or to the south or anything. It's just a number. Okay, so that's that. Let me just pause for a second. Okay, I also just want to say, so I'm going to keep going. We have 18 minutes left, which is a little bit less than 20 minutes left. So I'm going to keep going. I just want to gently remind you, or gently thank you in advance. You'll notice, so I'm going to move on in a sec. Well, here, I'll just so you know, I'm moving on to force myself to move on. Right. Just as a reminder, with 17 minutes left, you saw in the Google Classroom that it's time for course evaluations. I mean, evaluations of the professor. You'll notice again, you get points for doing that in this class. I don't want to see your actual value. I mean, I'm not allowed to, and I don't want to see your actual evaluations, and I won't see your actual. It's not my business. It's your business. But if you show me confirmation that you did it, right? I mean, even if you, whatever, if you show me confirmation that you did them both, you get 20 points, 10 for lecture and 10 for recitation, because technically I have you twice. I know it's a weird scheduling thing. Even if you write the exact same evaluation for both, since I'm the same person, fine. But if you do the evaluations, if you do both of them, you get 10 points just for doing them. And I just want to take this moment to emphasize, first of all, I will give you 20 minutes of class time on Wednesday to do them. To so that if you, but I, let me back up. I notice that some of you have already done them, and that's fantastic. And anytime you do them, you get the 20 point. I mean, as long as you do them, you get the 20 points. If you do it outside of class time, that's great. And you'll get the 20 points. And then if you come into class on Wednesday, when I take out 20 minutes, you could do whatever you want during that 20 minutes if you've already done them. But I will give you the 20 minutes to do them, because they are really that important. And you could tell even the way I talk, like, look, they make me nervous. I'm just admitting, okay? I've been doing this for a long time, and they always make me nervous because they do, because I just want you to know, because I do care, and because we actually do care, just so that you know, and I'm going to move on in a second. And I never know what you say as an individual. I promise. I don't know what you say as an individual, but we know aggregate, like what the evaluations say. And I want you to know that I'm on the committee that runs these evaluations that have been trying to improve them for years. We've been trying to improve the form for years. We have students on the, and you're welcome to join the committee, by the way. That's another thing if you want to talk to me. We have students on the committee trying to also improve the way we get the word out to students and trying to get students to know how much they care and I mean, how much they matter and in what way they matter. I promise they matter more than you think. They don't matter as much as they should, but they do matter more than you think. They really do matter. Enough that they always make me nervous, really. I mean, and I have tenure and all of that. I mean, but they really do matter. Your voices are heard. They should be heard more, but you also should hear more that your voices are heard on this. And you talk to each other through ratemyprofessor.com. That's fine, but that's you talking with one, and I know you care about that more, or I imagine, but that's you communicating with one another. If you want to get messages across to the administration about your faculty, I'm serious about this. If you want the administration to know what you think about your faculty, even if it seems like they don't care or it seems like you can't get faculty fired immediately just because you want to, like, yes, that is complicated, but believe me, as far as promotions and rehiring and all that kind of stuff, and especially with people that don't have tenure, like it does matter more than you think. And the committee works very hard to make it matter more and to change these documents, these tools, so that you have more of a say. Anyway, long story short, please do the evaluations when you get a chance. I will give you 20 minutes during class on Wednesday. You can remind me, I will. And or do them before, but you'll get points for doing them just because they do matter, even if they're all terrible. Like they matter. All right, enough. Hopefully that's good. Just raise your hand if I can move on. All right, I'm going to move on. Whatever. All right, I'm going to move on. But just so, but you can remind me Wednesday that we're doing them in class, that you'll have time. And then if you've already done them, then you can use the time to do something else. Okay. What I'm moving on now is, or just give me a quick hand if I can move on. I can move on, right? I think that, yeah, okay, okay, thank you, thank you, thank you. Okay, 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 thank you. All right. So now everything I just described, I have 13 minutes left, right? Everything I just described was the details of the vector business, which is an important detail. And but now, well, so now I've covered both those details that I've only defined, like what's the summary up here in the corner is I've defined that a small amount of work is the dot product of a force vector with a small displacement vector. So in more intuitive terms, that means a small amount of work is a force magnitude times a displacement magnitude, a distance, times the cosine of the angle between them. That's really the summary of everything I've said so far. But what I haven't then said is, why am I making such a big deal of small? Why do I keep saying small, small, small? Well, here's why. Because, like I said at the beginning, all of this can sort of make sense and sort of work as long as there is a force vector that you can multiply the displacement vector by in order to get the work scalar. We are saying work is force vector dotted with displacement vector, but that only makes sense if you have one force vector to work with. What if you have more than one force vector to work with? Wait, how could that happen? Well, if the displacement were large enough, right? Let's again look at this example right here. You know, it's like badly drawn. Look at this example right here. Imagine that the delta x were like a really big x. Imagine that it wasn't delta x, it was x. And imagine it was like 50 meters. So it's so big. I'm moving this box for so far across the floor that my push, the amount that I'm pushing it or pulling it, imagine that the amount I'm pushing it changes along the way. That's totally possible. In fact, that's totally much more realistic than any example we've said so far. The fact is, the farther you push something or pull something, the more there's a chance that you're not going to hold your push or pull steady for that whole time or for that whole space. So we need a way of dealing with what if what if the displacement is large enough that the force varies along the way? So the first thing we say, so here's how we deal with it. The first thing we say is Forces in physics obey a principle, an idea called superposition. Superposition means the whole is equal to the sum of independent parts. Like so many things in physics, this sounds almost obvious once you say it, almost obvious, but it's not obvious, or it's certainly not obvious that it's important. Or put another way, it might sound obvious, but in fact, it's not always true. Therefore, it's important. What do I mean? I mean, net force means the sum of the forces on an object, right? Like net force, back to old, net force equals mass times acceleration. Means like if I push you 5 newtons to the north while my wife pushes you 3 newtons to the south, right? So I'm pushing you with a force of 5 newtons to the north while my wife pushes you with 3 newtons to the south. What do we say? We say the net force on you is 5 plus -3, i.e., 2 newtons to the north. If I push you 5 newtons to the north while my wife pushes you with 3 newtons to the south, it is equivalent. The situation is exactly equivalent to as though someone had just come along and just pushed you with 3 newtons to the north, right? Now you might say, well, duh. Like, why do we even have to explain that? Like, obviously, 5 minus 3 is 2, or 5 minus 2 is 3, whatever. Yes, that the math is obvious, the arithmetic is obvious. But what's interesting about that, what's not obvious, what's not true in all situations in life or even all situations in physics, what's not obvious is what we're saying is the fact that I was pushing you with 5 is not affected by the presence of my wife pushing you with 3 in the opposite direction. In other words, I was pushing you with 5, and then my wife comes along and starts pushing. I'm just using my wife as an example, obviously, but I'm pushing you with 5, and then my wife comes along and is pushing you with 3. What we're saying is, yeah, I'm pushing you, and it's affecting you. And yeah, my wife is pushing you in the opposite direction, and that's affecting you. But my wife's push is not affecting my push. That's what we're saying. We're saying that forces superpose, that the whole result of all the forces together is like a big pot where each force is an ingredient, and each ingredient goes into the pot, and the presence of each new ingredient doesn't screw up the other ingredients in the pot. In other words, the ingredients in the pot, this is a metaphor, of course, but each force does not interact with any other force. A force is an interaction between one object and another, but it's not an interaction between one force and another. But one last final way, it's actually a deep recognition about the way the universe works. We're saying, I can push you, but I can't push a push. Do you see what I mean? Now, that's not always true. That's not true of all things in physics. Like waves, which we get to a lot in Physics 204, waves don't obey superposition. Waves interfere with each other. You may remember from 6th grade or 7th grade or 11th grade, waves like obey something called constructive interference and destructive interference. It can be like additive or it can be good or bad. But the point is, when two waves are like next to each other, they affect each other. That's not true of forces. Why? So it's interesting. Now, why am I saying? So I'm saying when it comes to forces, the whole is equal to the sum of its independent parts. The fact that forces don't force other forces, right? That's what I'm physically saying. The fact that I can push another object, but I cannot push another push. That fact allows for comparatively simple mathematics. It means that when it comes to a bunch of forces in a row, we can add them all up without too much difficulty, without having to worry about the very fact that there's a whole bunch of forces. So in other words, if you have a big amount of work, if you push something along a large displacement so that the force the entire time is not 100 newtons, but let's say for the first meter is 100 newtons, And then for the next meter is 200 newtons. And then for the next meter is 300 newtons. And then for the next meter is 400 newtons, et cetera, et cetera. What we can believe, and again, this is actually an important like breakthrough. It helps our math enormously. It's like a thank goodness kind of thing. We could say, oh, if you push something through an enormous displacement throughout which the force keeps changing in staggered steps, don't worry. We can say that the whole work is the sum of all the constituent independently contributing small amounts of work, all the parts. We can say that the total work, for an example like I just described, would be like 100 newtons times 1 plus 200 newtons times 1 plus 300 newtons times 1, etc. And just add them all up. And that would be the total amount of work. In other words, if we want to use good old mathematical notation that looks intimidating but is not meant to be, we could say if you want, so notice now, and I know we only have 5 minutes left. Notice now I'm saying work, big work, no delta anymore. Work in a big, work in a big interval, like over a large amount of displacements can be viewed as the sum of the works over the small amounts of displacements. Like, right? Like sigma just means sum of. Sigma I equals 1 means you set a counter to 1 and you say, look at the first displacement of 1 meter. Ask what the force is for that displacement. Do the dot product of the two. Put the product into your bag. Then ratchet up the I to the next counter, to counter number 2. Go to that next, to meter number 2. Ask what the force is for that meter number 2. Dot product the 2. Throw it into your bag and then ratchet up the counter again to I equals 3, right? And go all the way to N, where N is the last, whatever, the last value of I, the last meter that you have. So it's notation that you hopefully sort of got used to in math class. Again, secretly, I understand that some of you might still be intimidated by that notation, but it just means what it's trying to say that it means. It means sum of from displacement number 1 all the way to the very last displacement. Call it the nth displacement, right? So sum of from I equals 1 to I equals n, right? So it's just saying that a big amount of work would be the sum of all of the constituent small amounts of work, just like we would think. Again, this is, if you're thinking at all, I know we have 3 minutes. If you're thinking at all, oh my God, he's using so many complicated words to say something so simple. In a way, you're right. Like, good. If that's what you're thinking, that means you're getting the simple concept that I'm trying to get across, and that's good. Now, the truth is, the reason I'm using all these complicated words is because I'm trying to set you up for where it goes next. But yes, if you think I'm just saying that work over a large displacement is the sum of all of the small works making up that large amount, then you're right. That's what I'm saying. But now, with 2 minutes left, why I'm making a big deal of this is I'm saying, okay, but there's one step more we have to go. And we'll do most of this on Wednesday. I'm just going to set you up for this now, and then we'll deal with it on Wednesday. Wait a second, though. With 2 minutes left, in the realistic case of real life, that's not how things work. You don't like push something with 1 Newton and then go like a cartoon and then start pushing it with 2 newtons of force and then go like a cartoon and then jump to, like, it's not like a step function in real life. Usually what would happen in real life is your push would just get stronger and stronger or weaker and weaker continuously, right? Like what I'm really saying is, as long as you can take a big amount of displacement and divide it up into small sections for which each one has an identifiable, measurable amount of force, you're good to go. But in real life, that doesn't actually happen. You can't find a section of displacement small enough to capture one value of force, usually in real life, because usually in real life, the force is changing continuously. It's not changing in small but finite measurable steps, right? It's changing really in real life. Remember, in real life, it's probably changing over steps that are so small that we have to go to the limit as delta x approaches 0, right? So what really work really work, not delta W, not a small amount of work, but a big amount of work is really the limit as delta x approaches zero of the sum of f times the delta x's. Do you see what I'm saying? Now I'm going to pick up right from this moment, on Wednesday, and we'll do the class evals in the middle of the class. But I'm saying what we really have to look at is how do you take the sum of a bunch of products in the limit as the delta x of those products goes to zero? The answer that you might remember from calculus is called an integral. Where this is really going is work is the integral of f dot dx. The delta x gets swapped out and the dx's come in. That's what's going to happen Wednesday. If you see what I'm saying, great, you're with me. If you don't see what I'm saying yet, don't worry. I will back up and explain it Wednesday. But that's what I'm trying to say. And I just heard that beep, so that means, okay, so you've been very patient. You're being very patient in general. Really appreciate it. I'll hang out for any questions, but I'm turning off the record. Call me if there's any issues or text me if there's any issues. Thank you all again. All right, I'm stopping there. Yes, have a nice day, Samantha.